Welcome to the deep dive. Today, we're heading out into the cosmos, tackling something truly baffling, black holes.
Right. There's been a lot of curiosity about them, and we've got some great material, including insights from, a recent chat with Dr. Brian Cox. We're going to unpack what we think happens if you actually fell into one.
Exactly. We know folks want to get the real picture, but, without getting totally lost in the physics weeds. So that's the mission today.
What really goes down if you take that plunge? What would it feel like? And what's the latest thinking on what's inside these things?
Yeah, because they're described as, one of the strangest things in existence, a mathematical enigma. It's pretty wild stuff.
Truly mind-bending.
So let's set the scene. Imagine us, maybe you listening too, we're on this special spaceship and our destination, straight towards a black hole.
Okay, sounds like a plan. But maybe first, let's back up just a tiny bit. What is a black hole, fundamentally? And how did we even figure out they exist? They sound pretty theoretical.
Well, yeah, they started out that way. The basic idea is, imagine taking our sun, right, and crushing it.
Crushing it down really, really small.
Unbelievably small. Like, for the sun, down to a ball just, 3 kilometers across?
Something like that, yeah. If you did that, the gravity on its surface would just become immense.
So strong that the speed you'd need to escape the escape velocity becomes faster than light itself.
And that's the key, isn't it? Nothing, not even light, can get out once it crosses a certain point.
Initially, people thought, okay, this is just weird math, like a glitch in Einstein's equations, just theory.
Right, a mathematical curiosity. But then astronomers started seeing things, weird movements.
Stars orbiting nothing visible, galaxies behaving strangely, gas clouds getting whipped around by something unseen.
And eventually, the evidence pointed towards these things being real. These are the leftover cores of massive stars, much bigger than our sun, that collapsed at the end of their lives.
And they're not rare, are they? I remember reading some staggering numbers.
Oh, not at all. Estimates are maybe 40 quintillion of them out there in the observable universe. It's mind-boggling.
40? Wow. That's a lot of zeros.
And that's not even counting the supermassive ones. Pretty much every big galaxy, including our own Milky Way, seems to have one sitting right in the middle.
Okay, so let's head towards ours then, Sagittarius A. We've even got pictures of it now, sort of.
Sort of, yeah. It's important to remember the light we see in those famous images isn't coming from the black hole itself.
Because light can't escape it.
Right.
So what are we seeing?
That bright stuff, that's the accretion disk. It's a swirling vortex of superheated gas and dust, maybe shredded stars, all spiraling in towards the event horizon at incredible speeds.
Like water going down a drain, but way, way hotter and faster.
Exactly. It gets so hot from friction and compression that it glows incredibly brightly across all sorts of wavelengths. That's the light our telescopes pick up.
In the picture of Sagittarius A, it looks a bit like a donut, but not perfectly edge-on.
That's right. We're kind of looking down on it from above the disk, more or less.
But if we were looking at it edge-on...
then things get really weird because of the gravity. The black hole warps space-time so much that it bends the light coming from the disk.
So light from the part of the disk behind the black hole can get bent around it towards us.
Precisely. You'd actually see light from the back of the disk appearing above and below the black hole silhouette, maybe even seeing light that's looped around it. It's like a cosmic funhouse mirror.
Incredible. So our spaceship is getting closer to Sagittarius A.
Yeah.
How big is this thing, really? It's got the mass of, 4 million suns?
About 4.3 million solar masses, based on how nearby stars orbit it, which sounds enormous.
But physically, it's actually quite compact for that mass, isn't it?
Extremely. If you plopped it down in our solar system, its edge, the event horizon, would only reach about a fifth of the way to Mercury's orbit.
That's tiny. All that mass in such a small space. And compared to others, Sagittarius A is kind of average.
For a supermassive one, yeah. The size range is just staggering. You've got stellar mass ones like a J1650, maybe the size of Manhattan, but with nearly 4 times the sun's mass.
Wow.
Then there's one in Messier 15, about twice Earth's diameter, but 4,000 solar masses. Incredible density.
And then you jump way up. The supermassive ones. You mentioned one that's smaller than the sun, but 100,000 times the mass.
Right. And then there's M87's black hole, 5.4 billion solar masses. Our entire solar system would fit across it about 4 times over.
Okay, that's starting to get properly huge.
And it keeps going. ton, 618, maybe 66 billion suns. You could line up almost 40 solar systems across that one.
66 billion.
And possibly even bigger ones like Phoenix A, maybe 100 billion solar masses. And these are just the ones we've been able to measure. There could be larger ones still hidden.
It really drives home how extreme gravity can get. Okay, so back to our ship. We cut the engines, we're falling.
And initially, you feel nothing, just weightlessness, like astronauts on the ISS. You're in free fall.
We could be about to cross the event horizon right now, and we wouldn't even know it from inside the ship.
Exactly. But let's switch perspective. Imagine someone, maybe you listening, watching us through an incredibly powerful telescope from, say, 26,000 light years away. What do they see?
This is where Einstein's theories really kick in, isn't it? Time gets warped.
Massively warped. To the outside observer, our clocks would appear to slow down as we get closer and closer to the event horizon.
Slower. Slower. Until right at the horizon, from their perspective, our time pretty much stops.
Grinds to a halt. It's crucial. There are two totally different experiences happening simultaneously. Ours falling in and the observer's view from afar.
Because the black hole isn't just warping space, it's warping time too. Space-time, like that trampoline analogy.
Yeah, the bowling ball on the trampoline creates a dip that's gravity warping space. But it also affects how things move through time near it. A black hole is the ultimate dip.
So deep that even light can't climb out.
Right. Space and time are linked in this space-time fabric, and massive objects curve it. Black holes are the most extreme curves we know.
So, from our perspective on the ship, we just keep falling. But the outside observer, they never actually see us cross the horizon.
Never. From their viewpoint, we'd seem to freeze right at the edge, and the light from our ship would get stretched out redder and redder.
Redshifted, like a siren moving away.
Exactly. Redshifted and dimmer, fading away until we just disappear from view, never quite making it inside from their perspective.
It's like space itself is flowing into the black hole faster and faster.
That's a great analogy, like a river. At the event horizon, the river of space is flowing at the speed of light. Inside, it's flowing even faster.
So even light, trying to swim upstream, gets pulled in. No escape.
Escape is impossible once you cross that line.
Okay, but we did cross it in our thought experiment. From our perspective, we sail right through the event horizon. No bump, no barrier. We're inside.
Still falling.
Yeah.
Still initially weightless in that immediate sense, but uh-oh. Things start to change.
The gravity gets stronger, fast. And not just stronger, but differently stronger.
Right. That's the killer. The difference in gravitational pull between, say, your head and your feet starts to become enormous.
Because your feet are closer to the center.
Right. And that difference stretches you violently.
This is the spaghettification part.
It's
unpleasant.
It's a very descriptive term. You get stretched vertically, like spaghetti, but also squashed horizontally at the same time.
Stretched and squashed. Okay.
It's not gentle. First, the forces just become too strong for your body to hold together. You become a stream of, well, stuff.
Atoms.
Eventually, yes. But it doesn't stop there. The tidal forces become so extreme they rip the atoms themselves apart.
Seriously?
And then they rip apart the protons and neutrons inside the atoms. Even the quarks making those up get pulled apart.
So complete disintegration down to the most fundamental level.
Pretty much. Everything that was you and the spaceship becomes the stream of fundamental particles, all racing toward the center.
Towards the singularity. Now that's another weird concept. It's not just a point of infinite density, is it?
According to Einstein's theory, general relativity, it's more than that. Because space-time is so warped, the singularity isn't just a place in space, it's also a moment in time.
A moment in time.
Yes, it's the future. Once you're inside the event horizon, the singularity isn't somewhere you might go, it's the inevitable end point of your timeline. All paths lead there.
So trying to avoid it is like trying to avoid next Tuesday.
Exactly. You can't just steer away from it. It's the end of time itself waiting for you.
Wow. The end of time. That's heavy.
According to classical general relativity, yes, that's the end of the story. You're spaghettified, disintegrated, and hit the end of time. Full stop.
But then Stephen Hawking came along.
Right. And he threw a huge quantum spanner in the works. He realized, famously, that black holes ain't so black.
Meaning they actually glow. Emit something.
In a way, yes. Due to quantum effects near the event horizon, pairs of particles are constantly popping into existence. Sometimes one falls in and the other escapes.
And that escaping particle carries energy away.
Precisely. It looks like the black hole itself is emitting radiation, Hawking radiation. Very, very faint for big black holes, but it's there.
Which means they have a temperature And if they're radiating energy?
They must be losing mass slowly, incredibly slowly for large ones, but they are losing mass.
So they don't last forever. They eventually evaporate.
Over truly immense timescales, yes. They shrink and eventually disappear in a final burst of radiation.
Okay, hang on. If the black hole disappears, what happened to everything that fell in? Us, our spaceship, all the stars it swallowed, all the information about that stuff.
Ah, now you've hit the nail on the head. That's the information paradox. It's a huge problem.
Because physics says information can't just be destroyed, right? It can be scrambled, hidden, but not erased entirely.
Exactly. It's a fundamental principle. But Hawking's initial calculations suggested the radiation coming out was purely thermal random heat, with absolutely no information about what formed the black hole or fell into it.
So the information just vanishes? Which breaks the rules.
It seemed that way. It pits general relativity against quantum mechanics, the two pillars of modern physics. It's been a major headache for decades, like burning a library in the smoke, having no clue what books were inside.
So where are we now with that? Has anyone figured it out?
Well, it's still very much cutting-edge research. There's no final consensus. But there are some big developments around 2019.
Oh, yeah.
Papers came out suggesting Hawking might have missed something subtle. The idea now gaining ground is that the Hawking radiation isn't perfectly thermal.
It carries information.
Somehow, yes, in a very, very scrambled way. The thinking is that by the time the black hole completely evaporates, all the information that ever fell in is encoded in the total pattern of radiation that came out.
Okay, that saves the information principle, which is good. But how? How does information that went in, presumably hit the singularity, the end of time, get back out in radiation emitted from the horizon?
That is the multi-billion-dollar question. How does that work? The mechanism is, well, nobody's quite sure yet. It's deeply weird.
Are there, like, candidate explanations?
Oh, yeah. Some involve complex quantum entanglement between the inside and the outside. Others speculate about connections, maybe like tiny theoretical wormholes linking the interior to the radiation escaping outside.
Wormholes? Seriously, we're back to sci-fi.
Well, the maths allows for possibilities like that, though whether they're physically real is another question. Some even more radical ideas question if there even is an inside in the way we imagine it, or if reality is fundamentally just information.
Wow. It feels like black holes are forcing us to rethink everything.
They really are. They're these incredible theoretical laboratories where gravity and quantum mechanics clash. Studying them, these collapsed stars, these galactic centers, it pushes our understanding of reality itself. It connects to quantum information, maybe even quantum computing.
It's amazing. And the more you learn about this stuff, the weirder and more wonderful the universe seems. It doesn't make it less mysterious.
And not at all. It deepens the mystery, increases the awe. Knowing how strange it is makes it even more incredible.
So next time you look up at the night sky, think about that point of darkness at the center of our galaxy.
Yeah. Contemplate these objects, these distortions of reality. The more you understand nature, the more magical it feels, doesn't it?
Definitely. And maybe here's a final thought to leave folks with. If information truly isn't lost, even in a black hole, what does that say about, well, everything, about how connected reality fundamentally is?
It's a profound question. Really makes you think.
It certainly does.
Yeah.
Well, that feels like a good place to wrap up this particular deep dive into the rabbit hole, or maybe the black hole. Thanks for navigating that with us.
My pleasure. It's fascinating territory.
Absolutely. Okay, bye-bye, everyone.